Hello and welcome to Chapter 9, Endpoint Anti-Malware of ISOL 536 Security Architecture and Design. My name is Dr. Alan Dennis. I am your instructor. First off, the topics we'll talk about during Chapter 9 include a deployment model lens, analysis, more on deployment models, and then endpoint antivirus software security requirements. Jumping straight in, Chapter 9, Endpoint Anti-Malware. For the business analytics example, we know something about the protections, both technical and process, that were applied to the host and operating systems upon which the core of the business analytics system runs in that environment. Consequently, we discounted the ability of an attacker to listen in on the kernel level communications, most particularly the localhost intra-kernel network route. Additionally, if an attacker has already gained sufficiently high access privileges on the system to control processes and perhaps even to process memory, then it's essentially game over anyway, meaning that we're lost. Moving on to section 9.1, a deployment model lens. The user is installing antivirus software in response to the belief that the machine is already compromised. In other words, import security software must assume that, very similar to software exposed to the public internet, it is being installed into an aggressively hostile environment. Any assumptions about the operating system being free of successful compromises would cause the endpoint antivirus software itself to become a juicy target. At the very least, assumptions about a safe environment might lead security software makers to believe that they don't have to take the care with their security posture that, in fact, is demanded by the real-world situation. The foregoing leads us to ask two axioms. Assume active attackers may be on the machine even at installation time, and assume that attackers will poke and prod at every component, every input, and every line of communication. Section 9.2 is about analysis. In consumer-oriented products, the user will have the ability to turn security functions on and off. In corporate environments, usually only system administrators have this power. The user interface can take control of the security of the system. That, of course, makes the user interface component an excellent attack target. Likewise, the antivirus engine performs the actual examination to determine whether files and traffic are malicious. If the engine can be fooled, then the attacker can execute an exploit without fear of discovery or prevention. Consequently, a denial of service attack on the antivirus engine may be a very powerful first step in compromising the endpoint. To contrast this with the user's interface, if the attacker is successful in stopping the user interface, the security services should continue to protect regardless. On the other hand, if the attacker can stop the antivirus engine, she or he then has access to an unprotected system. Each of these components prevents an important target. The target offers different advantages, however. Testing shows the presence, not the absence of bug. That's a very true statement. You will only discover those bugs. You'll only know that bugs exist. You'll never know with certainty that something does not exist. Proving something is false or does not exist is very challenging. Continuing the discussion of analysis in section 9.2, the antivirus engine itself will have to be written to be as self-defensive as possible. Even if the antivirus engine validates the user interface before allowing itself to be configured by the user interface, still those input values should not be entirely trusted. The user interface may have bugs in it that could allow an attacker to take control. In addition, the user interface might pass an attack through to the engine from an external configuration parameter. The antivirus engine has another input. In order to determine whether files are malicious, they may have to be opened and examined. Most certainly in today's malware-ridden world, a percentage of the files that are examined are going to contain attacks. There is nothing to stop the attacker from placing attacks in suspicious files to go after any vulnerabilities that may lie within the file examination path. Thus, the antivirus engine must protect itself rigorously while at the same time examining all manner of attack code. In fact, the entire path through which evil files and traffic pass must expect the worst and most sophisticated types of attacks. The file open, parse, and examine code must resist every imaginable type of file-based attack. In figure 9.2, we can see that the system engages in communication with automated entities beyond the endpoint itself. Even if this were not true, a communique might be employed from intermodule communications within the system. In this case, the simple, immediately operating case, it would be a matter of design style as to whether to abstract communication functions into a separate module. The design was chosen in this case not only because the system does in fact support inbound and outbound communications as depicted in figure 9.2, but also for the reasons of performance. So as we can see here, there's inbound and outbound communication, and this is the basic architecture of the system. You have a driver operating inside of the kernel space. You have your antivirus engine that's in the user's environment, user interface that is interacting with the UI engine, and inside in a separate component is a file opener, the part that actually interacts directly with likely suspicious material. And then a communicator that is external yet that is used to communicate to external networks. 3.9, more about the deployment model. To make matters more complex, the validity of the update must be established such that it hasn't been tampered with between manufacturer and download at the endpoint. Integrity. In fact, most security vendors don't want the threat agents to have the details of what's been prevented nor the details of how protections work. At the least, these proprietary secrets are best kept such that uncovering them requires a significant work factor. Defense is better than if the attacker doesn't have the precise details of the strategy and tactics. The foregoing general requirement suggests that the communications should be confidential. This is particularly true when the communications must cross untrusted networks. If the updates are coming from servers across the public network or public internet, then the network would not only be untrusted, but also hostile. A working concept when considering the security of customer premise equipment is to understand that different customers require different security postures. Systems intended for the deployment across the range of security postures and approaches will do best by placing security decisions into the hands of the deployers. Indeed, no matter the guidance from the vendor for a particular piece of software, customers will do what is convenient for their situation. For instance, regardless of what guidance is given to customers about keeping the management console from your endpoint off of untrusted networks, customers will do as they wish. So the point here is that customers oftentimes do not do what's in their best interest. As such, you have to plan appropriately if you were designing one of these systems. Moving on to more on the deployment model. Before deploying new software, whether the updates are to the running module or to the malware identification mechanism used by the engine, the validity of the updates must be established. However, updates are obtained from dispersal by the management console, whether by downloaded from the software maker's websites or through some sort of push outwards to the management console. Attackers attempting to insert malicious code must be prevented. This validation could be done with a standard binary hash and signature. The hash value can be checked for validity. The signature will be made with the private key that can be checked against the public key for validity. This is the standard approach to the problem. And you'll see this oftentimes with lots of various software download, be it virus or antivirus makers or otherwise, is that they will oftentimes give you the hash code so that you can verify that the binary representation of the files is actually what was signed. For most organizations, any system having to do with the organization security will be considered sensitive and crucial or critical. As such, the parts of the security system implementing management of the system are typically considered need to know restricted system and interfaces. In particular, any system such as this management console that can change the security posture of other systems requires significant protection. Moving on to section 9.4, endpoint antivirus software security requirements. So start listing all of the requirements that are necessary for any antivirus software. Events and data flows from kernel driver to antivirus engine only, never from engine to kernel. Only the antivirus engine may open the kernel driver and only on system startup. Open is the only control operation allowed from the user mode to kernel driver. No other component may communicate with the kernel driver. The kernel driver startup and initialization code must validate, sanitize, and put into canonical order canonical form inputs from antivirus engine. The kernel driver initialization and startup must occur during the operating system startup sequence and must complete before users are allowed to log onto the system. Kernel driver initialization must complete before users log on to the system. Kernel driver initialization must occur as nearly as possible as soon as possible or as early as possible during operating system startup. So you want it to happen before other elements of the operating system start, in part because those elements could be compromised. Before communications are allowed to proceed between any two or more modules in the system, validation must be performed on the identity and integrity of the calling process, module, and binary. The preferred mechanism is validation of a digital signature over the binary. This signature must be signed by the private key of the software manufacturer. And again, secrets, keys, and certificates. Every other component except the kernel driver must run in user mode. Continuing the antivirus software requirements. Installation should confine the reading and writing of the configuration files to the user interface only. The system must have the ability to encrypt communications from to the management console. This must be system administrator configurable. The management console must contain a user authentication system, and the management console must contain a user authorization system. And the management console must be able to authenticate to an LDAP provider. Management console authorization must be able to be performed by LDAP group membership, and the administrator must be able to configure the management console to use any combination of local authentication, LDAP authentication, local authorization, or LDAP group membership. The user interface must re-authenticate the user before allowing changes. The management console will be able to run in a hardened state. There will be a customer document describing the hardening configuration. Hardening is configurable at customer discretion. So even though there may be an initial configuration that's acceptable for most people, there must be a way to make it even more secure. And the last conversation around endpoint antivirus security requirements. Input validation coding must be implemented on every system input. The particular care to file parsing and examination path, the reading of the configuration files and inputs from communicator, the file and event handling paths through the code must be rigorously fuzzed. All components of the system must be built using a rigorous security development lifecycle with particular emphasis on security coding techniques, input validation, rigorous proof of the effectiveness of the SDL, in other words, security assurance testing for vulnerability, and vulnerability testing before product release must be thorough and exploit multiple overlapping strategies of tools. Those are all pretty good list of requirements that are applicable certainly for antivirus software. Many of those could be reused for other types of applications that might have be a target for attackers in general. So you can take away and generalize some of these concepts, such as input validating coding must be implemented on every system input. That's a good idea everywhere. So rather than just taking something and blindly assuming that it is what it's supposed to be, so if you're expecting a date, making sure that it's a date of a certain length and so on, that's always a great idea. It's especially a good idea whenever you're doing something that is a really juicy target, such as an antivirus software. And with that, we've reached the summary for Chapter 9. As was noted, the list of requirements presented here cannot be taken as a complete list, since some of the requirements refer to previous discussions and are not reiterated here. For a real-world system, I would list all the requirements so as to create a complete picture of the security needs of the system. The architecture presented in this book, I'll reiterate, should be taken as an example, not as a recipe. So there may very well be things that are missing that should be added, but it's to show the idea of how this should be done as an example, not as this is how you would implement an antivirus software system. And as always, stay safe. This concludes our discussion of Chapter 9. I will speak with you again in future chapters.